you. And now, without further ado, it is time to introduce our speaker of the night, the famous, the amazing, the inimitable Bohan Zhang. Bohan is the co-founder of OtterTune. If you haven't heard of them, they are an AI-powered database optimization startup. I've been tracking them for a while. They're a cool company. And before that, Bohan, you said that you worked at Carnegie Mellon in their database group on the OtterTune research project, which was along similar lines, machine learning, and looking at applying that to particularly automated parameter tuning for database performance type of stuff. So Bohan has spent several years working around Postgres optimization for many customers, using both his domain knowledge and machine learning. He's spoken at a number of Postgres conferences in the past, including PGConf Asia in 2020, PGConf Asia again in 2021, Silicon Valley, so I was talking about last year in 2023, and we are very lucky to have him here tonight. Thank you for coming, Bohan.
Thank you, John. Thanks for having me here. Thanks for coming, Ivan. So today I'm talking about the part of Postgres we hate the most. Title is kind of controversial, but yeah, they have some title, and I wrote this. Actually, we have an article about that. They published on our website. So and my article, I wrote this article. It had lots of discussion on Hacker News. So yeah, today I will talk more detail about the part of Postgres we hate the most, specifically with the drawback of MVCC and how to optimize it. I'm Bohan, and Zhang is the founder of OtterTune. So OtterTune is a startup based on many years of research from Carnegie Mellon University, database group, led by Professor Carlo. So we use AI and machine learning to automatically optimize the Postgres and MySQL to improve performance and cut costs. So let's get started. So I will first introduce the background of the MVCC and how MVCC implemented in Postgres. And third, I will discuss the problems caused by MVCC and optimization on that. And then last day I will talk about some case study from our real-world customers, talk about real-world examples from our customers. So background. So without Postgres, without it, because it's a fraud decoder database based on BBNG20, and it's also actually a normal popular that you might think. Actually, in OtterTune, we have roughly the same number of Postgres and MySQL under our management. So it's very surprising because the number of Postgres and MySQL is roughly the same from our customers' data. So yeah, its popularity has been significantly increasing over the last 5 years. Is this trend still continuing? So I think it's because of several things. The first is open source. I think how much time I did lesson. The feature rich is extensible, and the also the common storage. So I think there are also many open source projects based on Postgres. For example, the TypeScript is a TypeScript database based on Postgres. There are many the ecosystem is really good for Postgres. And also there are top providers with less heavy Postgres. For example, Google DB is also based on Postgres, and Redshift is all that query engine based on Postgres. So Postgres is really popular space. But certain aspects are not that great in Postgres. As much as we develop Postgres, like at OtterTune, certain aspects are not that great. So instead of talking about how awesome Ariana's query database is, today I'll talk about the one major thing that sucks, which is multi-version control and MVCC implementation in Postgres. So our research at CMU and our experience of Postgres at OtterTune has shown that MVCC implementation is the worst among already used Postgres already used databases that MySQL. So MVCC can cause some severe performance issues for some workload. So we'll discuss this. So what is MVCC? So when the query updates an existing row in the table, the database makes a copy of that row and applying changes to the new row instead of applying changes to the original row, or write the data to the original row directly. So why do you want to do this? This is because in this way, the readers will not block writers, and writers will not block readers. They can increase the data throughput and also reduce the latency. So otherwise, if you write to the original version of your data, right? If you will write the data and then you have a query with the same data, you need to have the log to block the queries. With MVCC, the writer will not block reader, and reader will not block writer. So that's why we have MVCC, implement MVCC. But there's no free lunch. It introduces additional overhead and issues. For example, you need to maintain multiple versions in your storage, and with data, you need to find the latest version of your data because you have multiple versions. So you need to find the latest one, right? And you also need to clean up the old versions which are not used anymore. So all this introduces additional overhead and issues in MVCC. So how MVCC implement Postgres? We'll use a simple movie table as an example. So you can see there is a full movie table. So there are 3 rows. There are 4 columns. The first column is ID, the second one is name, and the year of the movie and the director of the movie. So we have 4 columns of the movie. We have 1 primary index on ID, and 2 secondary indexes on name and director. So yeah, this is a movie table. We use this as an example. We have 3 rows. The first one is short and return, so we will use this movie as an example. So let's say update this movie, right? So we update this update the year of the movie from 1985 to 1983. The query is above. So how Postgres do that? So first, Postgres makes a copy of that row. So it makes a copy of the first row, right? You can see on the right table. The first row is the old one, and it's make a copy of that. So it's have that at the bottom. So it makes a copy of the row and compile changes. We change the year from 1985 to 1983 on that table. So we have old version, we have a new version. So all versions in table are stored in the same storage space. This is known as the path-only version storage schema. So the next question is that because we have multiple versions in the storage, how to find the latest version when we read the data? Let's say we have a query, so we want to get this movie data. So the idea is that we have pointer from old version to new version. So in this table, we can see the first row is old version. It points to new version. So each table version points to new version, and head is the oldest table version. Then there is a version chain, right? It's known as oldest to newest version chain. This is the old version points to the new version. So in our databases, we have a different implementation. It may use oldest to oldest version chain, which means the new version points to old version. And in Postgres, they use oldest to newest version chain. So to get the latest data, the Postgres needs to traverse this version chain. It starts from the head, and then it traverses the version chain to get the latest one. This is how the Postgres get the latest data. So the thing is that if there are many versions in Postgres, so you need to traverse the whole version chain to get the data. If the version chain is too long, the performance is not good. So Postgres has indexes. So idea is that when we update a row, it also adds an entry in your index. So basically, in this example, there are 2 table versions, the old version and new version. And in index, so on the left side, it has for each version it has an entry. So the version 1 point to the old version 1 and 2 in the index point to the new version. So in this way, when you fetch the data, you can from index you can get the latest version directly from index because it has a pointer to the latest version. So when you read the index, you find the latest version. You find the entry point to the latest version, and you can get the latest version. In this way, you can watch version in the version chain, but there is overhead maintaining the indexes. So actually, for each physical version of row, we need to add Postgres add an entry to array tables index, which means if so in this example there is an index on the moving name. So when update the row in this table, you can entry in this index. But if you have multiple indexes, you have like 5 or 10 indexes, and you need to add an entry for all of the indexes. So this introduces additional overhead. So the index avoid having to traverse the entire version chain to get the version that introduce the index maintenance overhead and rest amplification. Because for the same data, you have multiple entries for each version. So it has the rest amplification. So to solve this issue, Postgres has a optimization called hot optimization, which is only tuple optimization. So this optimization can only be applied to the hot updates. So what is a hot update? So a hot update hit only tuple update. So this is an update which does not modify any columns referenced by any indexes, any table indexes. And the new version is stored on the same data page as the old version. So for this example, we can see we update the year, the column year, but for this table we don't have an index reference to on the year column. So the column is not referenced by any table's index, and the old version and the new version are stored on the same data page, which are on the table page 1. So this is a hot update. So for hot update, we have such optimization. So for hot update, we don't need to add any entries in index. So we still have an entry point to the old version. So then in this way, we don't need to maintain an index. Also, during normal operations, Postgres will remove the old versions to print the version chain. So in this way, we don't need to maintain an index, and we don't need to have too much index maintenance overhead. We also print the version chain so that we improve the read performance, because the version chain, the depth of version chain is reduced. So this is called hot optimization. And of course, Postgres has to remove the old tuple versions, right? Because we need the Postgres has the auto vacuum process, which is triggered regularly to clean out the data tuple, to remove old versions that no longer need for users. So Postgres uses a regular procedure to clean out data tuples. And you can see in this figure, it shows the number of data tuples. Data tuples means the expired versions of expired version in databases, the old version in your table, the total version in your table. And so the number of data tuples drops regularly, every day, regularly. Because this is because the auto vacuum clean up the data tuples and we keep storage space. We can say the auto vacuum is triggered regularly. It cleans up the data tuples automatically. So now we know how MVCC is implemented in Postgres. We'll discuss what's the problems that are caused by MVCC. We already mentioned some problems, before that look at these problems and how can we optimize it. The first problem is version copy. So when a query updates a tuple, all of the columns are copied from to the new version. So in this example, we only update the year, the column year. It's just one column, but you can say we need to copy all other data, right? We need to copy all the columns into the new version. So let's introduce the massive data duplication and increase the storage requirements. So in this example, it just has 4 columns. What if we have 1,000 columns in the table? That's a very huge overhead. So unfortunately, there is not a good way to solve this issue. Because to solve this issue, you need to rewrite your underlying storage engine in Postgres. There's no easy way to have this. I think there's an open source project or DB. They are trying to rewrite the underlying storage engine in Postgres to avoid this issue. But as far as I know, there is no easy way to solve this issue in Postgres. The second one is table build. So the database has to load that tuples into memory for execution. So in this example, we can see the database has nine tuples. 7 of them are data tuples, and 2 of them are data tuples. So in theory, we don't need with the data tuples. We don't need the data tuples. However, the database with the smallest unit can fetch data in memory. So in order to read those 2 data tuples, you need to read all tuples into memory. Which means it also need to read 7 additional data tuples into memory. So this means you basically need to fetch more data than necessary into memory. It can introduce increase your read IOs, and it causes the database to incur more IOs during the read, and consume more memory than necessary during those steps. And it can also lead to inaccurate optimized statistics. Because, for example, in a table, if the table only has, for example, 1,000 rows, and then it needs to fetch 10,000 rows, 10,000 to memory because of that tuples. So it's not accurate because the optimizer thinks it only need to fetch 1,000 rows, but in theory it needs to fetch 10,000 rows in memory. So there is a mismatch between the statistics, and the inaccurate statistics can lead to a bad query plan, and it can also lead to a bad query slow query performance. Actually, we have an example for this here. To solve this issue, so Postgres has the run auto vacuum. We can also run on vacuum manually by yourself. But the thing is that for vacuum, it only remove the data tuples, but it does not reclaim the storage, return unused space to the operating system. So in this example, you can say we have 2 data pages, and we remove the data tuples in the data pages, but we still have 2 data pages. It cannot retain the return unused space to the operating system. Instead, we can use the vacuum full, which is this command will not only remove data tuples, but it will also return unused space to the operating system. So in this way, it will create a new data page and just get the data tuple in data page 1 and data page 2 and write to a new data page, and remove the original data page 1 and data page 2. In this way, it can return unused space to the operating system. But the thing is that that is very time-consuming and resource-intensive. So you don't want to run vacuum fill. You need to run vacuum fill carefully. You don't want to run it on, for example, peak time. You need to find some time when traffic is low and run vacuum fill. And also, it's a block other. When you run vacuum fill, I think it locks the table. It's a block other operation for that table. So for this, we should monitor the database loads using some statistics. For example, I think there is an extension called PostgreSQL. So we can get the load ratio for the tables. We should continuously monitoring the table load. And if the table load is large, which means there are too many data tables in the table, we want to retain unused space using vacuum fill. So there is a package called PostgreSQL. That one is an online version of vacuum fill. So when you use that, it will not block other operations. It is online version of vacuum fill. So this is a table problem and some optimizations on that. So the third one is index maintenance. So as discussed before, for non-hot updates, Postgres needs to modify all indexes in the table for each update. So if you have dozens of indexes, you need to, for a single update, you need to maintain all of the indexes in the table. It introduces significant index maintenance overhead and rectification. So we analyze the data from our customers. We find that actually roughly 46% of updates use the hot optimization on average, which means still more than half of the updates are not hot updates, which means those updates can introduce significant index overhead. So this means we need to carefully design your index. We need to remove the unnecessary indexes. The more indexes you have, the more overhead you have during updates. So we should drop the duplicated and unused indexes. We should also be careful when adding an index. So for some of our customers, they just find a store query and they just add an index to improve a single store query, but it actually hurts the performance of all other queries and introduce the overhead for maintaining indexes. So when adding an index, you need to be very careful because it can introduce other overhead. Our team automatically detect such unnecessary indexes by using statistics on each their own indexes in Postgres. So I think there's a blog article from Uber discussed by why Uber switched from Postgres to MySQL, and it generates lots of discussions. I think index maintenance is one main reason for Uber to migrate from Postgres to MySQL, because I think for their workload, I think it's a web-heavy workload. So basically, lots of updates in their workload, and which means lots of investment overhead for them. So they migrate from. That's one of the main reasons they migrate from Postgres to MySQL. They have an article here. So side comments is that about actually the Postgres is ordered to units version chain instead of units to oldest version chain step in the block. So it's in the block is state that is units to oldest, instead it should be oldest units version chain. The last one is vacuum management. So auto vacuum is the process which periodically and automatically clean up your data tuples. But making sure the auto vacuum is running as fast as possible is very difficult due to its complexity. For example, the default setting for tuning the auto vacuum are not valued for all tables, particularly for large tables. So the auto vacuum skill factor, the default value is 20%, which means if you have a 20% DAG tables in your table, auto vacuum will be triggered. But for large tables, it's not good enough. Let's say you have 100 million tuples. So it needs 20 million DAG tuples before the auto vacuum kicks in. So there are lots of DAG tuples. Before the auto vacuum kicks in for large tables. So ideally, we should fine-tune auto vacuum setting at the table level. So for large tables, we should decrease the skill factor so that it will kick in auto vacuum earlier for the large tables. So for in Postgres, actually, you can set the auto vacuum setting on the table level. Yeah, so we should fine-tune the auto vacuum setting, particularly for the large tables. Another thing is that auto vacuum can be blocked for several reasons. One main reason is the long-running transaction. Those long-running transactions will block the auto vacuum, block the auto vacuum process from cleaning up the DAG tables. If you have long-running transactions, vacuum will get blocked. And it will introduce more DAG tables and inaccurate statistics. And then it will generate more slow queries. So this means that it's a vicious cycle and make your data store less slower. You have more non-transaction, you have then block the auto vacuum, and then you have more DAG tables, and then it introduces more slow queries. So your data will get slower and slower. Actually, we have a customer. Actually, we have a customer. They have a bug insertion. And the statistics, the optimized statistics is not updated on time. So the beginning they have bug insertion, and the number originally the table had 10 rows. And after bug insertion, it has 1 million rows. And the optimizer still think it has 10 rows because the statistics is not updated. So it run a synchronous scan on table because it only has 10 rows, right? And not just synchronous scan on table. So it generated very bad for that. Because in theory it has 1 million tuples in a row. So the synchronous scan is not good for running table. So that's how. How the issue comes from stale statistics. So to solve this issue, we need to run ls manually. Ls will manually update the statistics. So for every bug insertion, we should run ls manually to update statistics on time. So after doing this, the long queries execution time went from 32 minutes to just 34 seconds after optimization. So this is a real world example. So we need to identify and resolve non-run transaction properly. So for this vicious cycle, we need to request human to find the non-run transaction as soon as possible and kill those non-run transactions. Or find the issue why it has those non-run transactions. In this example, we find that we need to run ls for after each bug insertion. So this way it requires the immediate command interventions to identify such non-run transactions and kill this transaction or improve this transaction performance. We should also use statistics to identify the long vacuum process. For example, if the vacuum takes too long to finish, we need to identify the process and try to optimize that. So lastly, I discussed some case study. Those are real world examples from our customers. So, the first one is one of our customers. They find the huge hidden spikes on March 22nd. I think it's last year. So they find a huge latency spike. The latency increased from P99 per latency, increased from 12 milliseconds to 1 millisecond. This is a 90 times increase per latency, and they don't know why. So they come to us, and we look into their metrics, and find that the update queries, the number of update tuples, this queries, it's roughly the same during the spike. So it dropped a little bit, it dropped 25%. So the originally is 53,000 update tuples per hour. It dropped to 40,000 update tuples per hour. It's not at all. So we found that it's an update heavy workload. And it only have few insert and delete queries, so we can ignore the delete and insert queries. So we think there's something wrong with the update the update queries, because the throughput dropped a little bit, dropped 25% for the update queries. And we also find the latency for update queries increased from 12 milliseconds to 700 milliseconds. So it's 60 times difference increase for the update query latency. So it's an update high workload, and during the spike, we think there's something related to update queries. So then we look into their data tables, number of data tables. We see the number of data tables increased a lot. So it increased from 65,000 to 40 million data tables. It's 600 times increase for data tables. However, the update queries, the number of update queries are not changing at all. The data table is not because of you have a huge update during that time. Instead, the number of update queries are not changing at all. But the data tables increase by 600 times. So we think the tables were not actioned successfully for this customer. And consequently, more data will react from memory and disk. So we also look into the number of read blocks. We found that 375 times increase for the number of read blocks, which means we need to read lots of the data from memory and disk. It's all because of the number of data tables, right? Previously, we only have 65,000 data tables, and then it has 40 million data tables. It needs to read lots of data tables to memory during table scans. So that's why the number of the read blocks also increased a lot during the spike. Interestingly, we also find the number of hot updated tuples equal to 0. So previously, around 99.9% of updates queries are hot updates. That's the optimization we mentioned before. Is use hot optimization for the updates. During spikes, it dropped to 0%, which means all of the updates are non-hot updates, which are more expensive than hot updates. So the updates were more expensive during spike time because the hot optimizations were not applied during that time. So finally, we found that there are some non-running queries blocked for auto vacuum on March 32nd, and then the data tables accumulated. The number of data tables increased by 600 times. And leads to a significant increase in block reads, which increased 375 times, and the non-hot updates also increase. So during the spike, all of the updates are not hot updates, which means the hot optimization cannot be applied to those updates. The updates become more and more expensive. And this leads to according to the spike, right? 90 times increasing peanut accuracy. So how to solve the issue is that we identify some unknown queries and just to make sure it does not happen in the beginning. We improve the performance of the unknown queries or kill those unknown transactions, and then it's the automatically resumes and it works properly after that. So there are also some interesting findings on auto vacuum. The first one is that is auto vacuum really vacuuming the table? So in this example, so there is a metric called last auto vacuum. This metric indicates the last time this table was vacuumed that auto vacuum demo. So this time that is last time when the table was vacuumed. So in this one, in this figure, the dashed line shows the timestamps the table was auto vacuumed. So this metric shows this table is vacuumed regularly, but however, the number of that table increases continuously. It's not job, which means although the table, the statistic shows the auto vacuum is executed, but it does not vacuum the table successfully. So this figure shows the number of that table. You can see increase from 0 to 20 million, and during this time there are many auto vacuums are executed. But those auto vacuum does not vacuum the table successfully for some reason. So last auto vacuum, this field keeps updated, but the tables are not successfully vacuumed. So this is an interesting finding. So we want to know why does this happen. So the thing is that even if there's some non-running queries block the auto vacuum, the auto vacuum will still be executed successfully, but it does not remove any data. So we can say in this example, we tested locally use a simple table called public.path. And we run a long query to block the auto vacuum process. But we can say this is the log of the Postgres. We can say auto vacuum is still executed successfully. However, 0 pages are removed, 0 tables are removed, 3,870 are that table, but they are not removable because of there is the non-correct block the auto vacuum process from removing them. So we can say the auto vacuum process is still executed, but it cannot remove the data tables. So that's explain why we have the auto vacuum reflections here, but the number of data table does not join. So this means even if an auto vacuum fails to remove any data tuples, this timestamp will still be updated. So which means we cannot depend solely on this timestamp, but that's auto vacuum, to know whether data tables have been removed or not. So we can not only rely on this metrics to say whether your auto vacuum is optimal or not. So this is one very interesting example from our customers. Another example is that the dash lines are still the timestamp when auto vacuum are executed. We can say the number of dash tables increase. However, there's no auto vacuum running during this timestamp, during this time range. So what happened here? So auto vacuum was not triggered on the table during this time range. So what happened here? So when looking into their table metrics and auto-vacuum metrics, they found that there are those auto-vacuum workers affiliated with auto-vacuum other tables. So there is a parameter called auto-vacuum max workers. This parameter specifies the maximum number of auto-vacuum workers that may be running at the same time. So default setting is 3, which means you can only have 3 auto-vacuum workers, 3 auto-vacuum processes run on the same time. So if we found that in that case, all 3 auto-vacuum workers are affiliated with vacuuming other tables. That's why for that table, auto-vacuum is not triggered because you can only run 3 auto-vacuum workers, and those all 3 auto-vacuum workers are affiliated with vacuuming other tables. There are 2 ways to solve this. The first one is that you can just increase this number. So if you have more auto-vacuum workers, you can basically have more chance to get vacuum because you have more auto-vacuum workers. Another one is that you can just speed up the auto-vacuum process. So if you run that auto-vacuum faster than before, you have more free time to vacuum the table. So there are some parameters to actually control the speed of the auto-vacuum process. The one is vacuum cost per day. Then another one called vacuum cost limit. So the idea here is that the Postgres has a cost model to calculate the cost of your auto-vacuum process. If it reaches a limit, it just sleep a little bit, and then we run auto-vacuum process. So this factor, cost limit, control the limit. So when the cost of auto-vacuum reaches a number, it sleeps this number, this second law. So this one cost delay, you can increase this. Sorry, some error. It should be decrease this. Decrease this. We should speed up the operation process, so we should make the state shorter. So we should decrease this value, and we should make the limit longer so that you have more time to run auto-vacuum. So we should increase this value. There's something wrong with my understanding. So we should decrease this value to make the state shorter and increase this cost value. And yeah, that's it. So if you want to tune your database automatically with auto-tune, just try this, and you can try it for free. I respond using Postgres and SQL, both the Lua, RDS, and service. If you have any questions, just feel free to reach out to me. This is our address. Thank you very much. Happy to answer any questions.
Back to your first case study, the takeaways from the first case study, I was confused. Yes, right there. Are you saying that the dead tuples accumulating cause non-hot updates?
Yes, this is a very interesting thing. In this example, yes. But I'm still trying to figure out why it happens. But actually, I can reproduce with a simple TBC code. I can reproduce this. So, yeah, I'm still trying to figure out why this happens. It's not always happening, but that happens for this customer. And I can reproduce with TBCC.
It could be space, might be one reason. Because for hot updates, you have to have space on the page. And if you can't clean, you're going to run out.
Okay, that makes sense.
I mean, I'm just guessing. That's just one possible idea.
Sense, yeah. Because a hot update can't split a page. That's the same as a page.
It can't jump to a new page.
Okay.
Yeah, that makes sense.
But I have no proof. I'm just like,
That's something that makes sense. I couldn't think of why else you have, other than changing the workload.
But in that case, just a vacuum will not help, right? You will need to repack or vacuum full.
not even, none of that. In this case study, none of that would do anything.
You would effectively get more space on each page after that.
Well, like all the way at the top, right? I I mean, like, just you can run vacuum all you want, because in this case, vacuum was running all the time. And
Yeah, I mean, you wouldn't get to run it, yeah, sure.
so until you, if you have a, gosh, I can't believe that was really like over 24 hours. I'm curious, do you know, like, was it an outage for them? Like, what the impact was? Did they scrape by? Like, was it kind of a non-critical system? Or that was such a long period of time. Whenever I see a chart like that, I was saying earlier, like, I know I'm gonna have a very bad day.
I'm always thinking, right?
Maybe that's what happened to LinkedIn yesterday.
That happened last year. Anything you have a huge spike and you want to know why. And you want to make sure it's not caused by others too. So we make some configuration recommendations. So I'm looking into the data, I told them, oh, it's not because of that, it's not on queries, blah, blah, blah. They say if you can like make it analysis automatic for them, it should be a very good feature for them. Yeah, so I think can reproduce this locally. I'll probably write a blog about that later if I find something. If I find why it happens. But it did happen to its customers. Yeah, it's very interesting. Yes.
One question. You had a slide that you talked about Uber, I believe, like
Yes.
migrating from Postgres to MySQL. I don't know if I missed it in your presentation, but is one of the reasons because of how Postgres handles MVCC and MySQL handles it differently?
The one reason is because of indexes. So for Postgres, as I mentioned before, it has a index overhead. In that overhead, when I update tables, I think for MySQL, they have different implementation and MVCC, so it's more efficient than Postgres for that workload. Yeah.
That's 2016. You can see it on the slide. And I think Uber subsequently switched from MySQL to something else. They like to switch.
I think the original story is that they switched from MySQL to Postgres, then switched back to MySQL. Yeah, please.
So I'm not really used to using replicas, but if you use a replica, the replica will also have the vacuum problem on it? Or can we have long queries running on the replica instead of master copy to avoid the problem?
So the question is that if you have a read replica, does the read replica also have a vacuum problem? Probably not, because it's a really
You can
only.
you can if it's a it depends on how the replica is configured. Because at some point the primary will push down saying, hey, this is going away now because I don't need it anymore. But if the replica reading that, there has to be something that gives. So if the replica can tell the primary don't do that, that'll possibly or just kill train. So the replica can kill the query.
Maybe I put this manifest this overlap.
That happens too.
But for answer ideas, for read replica, I think it's read only, so you cannot run vacuum on read replica. But I think if you have more efficient vacuum on the record, and it's, I think that probably the replication time will be reduced for reader. That's my guess. But for read replicas, I don't think you have permission to run the vacuum process on reader. And vacuum nodes should not work on the read replica as well, so it works on the record. Yes, question.
Very simple question. So if I have an RDS on a Postgres, which is a private subnet, so essentially it's not exposed to the internet. So how often is it going to talk to that particular instance? Do we have an EC2 interface or any serverless interface for the operating agent to talk to the RDS?
So to talk to RDS, so for orchestrating has an agent within a network. So the agent only collect the data, collect your metrics data. They don't collect any user's data. So just get the table metric, those metric data some contributors, members, etc. to track those data and send the data to us. So that is don't need to be public, right? You just need to install an agent within your network and post data to us.
So basically, like any interface we need, any SQL instance or anything like that.
So right now we only support automatic tuning from now. So we have some in-depth code recommendations, but it's not automatically applied to our database. We can only apply the not changes automatically. So we talk to RDS with using some APIs, RDS API, OI APIs. It allows us to call use this API to change the knobs, change the configurations, but you still need to run as permission to do that. Yeah. This question.
Are there sort of equivalent problems along these lines with, like, if you've got an insert heavy or appends heavy sort of workload, or is this more specifically a problem for updates?
So for index maintenance, sorry, for which one is specific for updates?
Well, like, would you have these kinds of problems if you're primarily inserting new rows rather than updating existing ones?
Okay, so the question is that if your workload is inter heavy instead of public heavy, the issues I mentioned here will still be an issue for inter heavy workload. I don't think so because we don't actually have tuples around. So
Yeah, this seems sort of updates.
yeah, yeah. So it only happens when you have multiple versions of the tuple. It only happens when you update your tuples or delete your tuples. If you only have inter queries, I don't think it can be an issue.
Yeah, so is Postgres like also significantly slower, you think, for sort of append-only type workloads, or is it more similar, not as much of a delinquent there?
So I think Postgres is really it's a RTP that is, and I think for most of our customers, those are really heavy workload. You have lots of read queries, and if you are write heavy workload, there are some organizations such as LSM3 or those SDB, those are probably optimized for write heavy. I don't think if you have write heavy workload, Postgres will be an issue. But for most of our customers who use Postgres, these are really heavy workload because they can spill the workload with the replicas. If you are heavy, that's an issue here. You cannot spill the writer, but you can spill the queries with the replicas. Yeah. So for that heavy workload, actually some of our customers they have lots of that queries. And they do find the replica with RDS cannot handle that because it cannot scale the writer, it cannot scale the reader. So that is some distributed solutions, for example, PostgreSQL, KDB, those kind of distributed SQL, which can in service scale the write efficiently. Yeah, so for Postgres, most of our customers are really happy.
When you talk about book detection, you mentioned PGStat tool. Is PGStat tool, that one, is it expensive to run?
Oh yeah, that's a good question. Actually, it's expensive to run with PGStat tool if you want to get the accurate number. I think there are some estimation, there are some, you can get a rough estimation with this module, but it's not too expensive to run for that case. But if you want to get accurate number, right, I think it's expensive to run to get accurate data slope ratio. And there are some estimation approach to estimate the slope ratio. But trade-off is it's not accurate enough. But it's very fast to run. But I don't think you want to run this table for large tables in production. You should run this very carefully. It takes time.
We had issues that we used to use a lot. They were
question about order view.
Yeah.
When you detect that you want to change a parameter for some reason, so like, is it only limited to dynamic parameters or to static parameters?
Yeah, that's a good question. So in order to, the question is that for order to, does it only change the dynamic knobs or is also change the static knobs? So the answer is that we start from the research project, which we can run we can run MVCC and we start there with our families. So we tune both the dynamic and static knobs in the research paper. And then we build this product and we have a feature that user can also change the static knobs. By the way, static knob means that after changing knobs, we need to restart the database to be effect. Then dynamic knobs that if you change the knobs, they can be effect immediately. So at the first origin stream, is suppose static knobs, but we find nobody is using that because nobody is restarting the production database for just changing changing the knobs for recommendation and recommend that origin. So just copy that feature. So right now we only support dynamic knobs, but it should be good enough for most of the customers. Yeah. And I think more and more knobs are dynamic these days because in Postgres and SEAPUG, because they want to make it more dynamic. Some knobs are static in the old version, and right now it's dynamic in the new version. So for our customer, I think dynamic knobs are good enough.
Another origin question. So I feel like the one Postgres configuration that there's the most information but also inaccurate information about tuning online is shared buffers. I'm curious, in your experience, like what is actually the right calculation for that?
So the question is that what's the accurate calculation for shared buffer? I think Amazon said before as 80% of memory. It should be good enough for most cases. But if you want to fine tune this knob, it really depends on your workload. So that's how origin works. It's for different workloads, the default settings are not optimal. So origin should make recommendations for different workloads. So basically, train data, attaching data for each different workload, and make recommendations based on that. So it really depends on your workload. Different customers have different workloads, so they have different optimal settings. But for that one, I think Amazon said to 80%, it is good enough for most of the customers, the users.
So just to clarify that number is just like 80%. It's and Amazon didn't come up with that. That number goes way back further. Like that, even in the Oracle world, like in the 2000s and 90s, there was kind of this rule of thumb, like 75-ish%, 3/4 maybe, used for database cache. But it's all very. There's not tons of science behind it. There's a lot of room to tune for workloads. So I'm curious, just following on Tommy's question, yeah, like are you guys able to tune that for workloads with Otter?
We do tune that for, but not for that specific node. You do can tune the shared buffers for different workloads. So how Otter works is that for each workload, for each customer, it collects the data from that customer. So basically, those data are trained for the customer specific workload. So they can make recommendations, optimal recommendations based on your workload. So yeah, but we really do not tune that shared buffer that much because it's 80% is good enough for most of the customers. And the thing is that it can cause some issues if you cannot set it correctly. Because if you set it to a low value, it can cause some issues if it runs out of memory. So that's why for some knobs we don't train it by default. That's the reason. Any questions? Cool. So this one is my this one is my email address, and you can try. I'll put that for free. Thank you.
Thank you.